Hi everybody, and welcome to the second video on arrays. In this video we simply continue the trajectory of study that we began in the last video when we introduced arrays. So in this video we're going to just do a few things. I'm going to talk about how you can format the way that an array is printed to the screen. I'm going to talk about how you can get the array from the user. So rather than filling in the entries of the table yourself, how do you systematically get the user to give you the table's entries? I'll show you an example or two, and then at the end we'll talk about higher dimensional arrays. So these three items here refer to two-dimensional arrays. So at the end of this video we will turn our attention briefly to higher dimensional arrays. Okay, so the first thing I want to talk about is when you print an array, how do you get the columns to line up in an aesthetically pleasing manner? So here is the array I had from the last video, and it's printed out down here already. It prints out the numbers 1 through 100, and it goes 10 numbers at a time in a given row. So this code right here is just the same as from the last video. You march through the table row by row, and inside each row you go entry by entry, and you save 10 times the row number plus the column number plus 1. And that goes in entry ij. So what this for loop does is, when I is 0, you enter this inner for loop here, and I is 0 the entire time. I is keeping track of the row number. So the first time you do this inner for loop, you're in row 0, and I is 0. Right? 10 times 0 plus the column number plus 1. That's what goes in the given entry. And then once you're done with this for loop in here, the value of I increases by 1. So now I is 1, so now you're in row 1, which again, confusingly, is the second row, and so on. So again, this code is not new here. This is what we had last time. Notice that when I print though, when I print it to the screen, the columns don't really line up. You know, you'd like for this 1 to be directly over this 1, and this 2 to be directly over this 2, this 3 to be directly over that 3. You know, you want the columns to line up. So the way that you get the computer to do that for you is first you include a library called IO_manip, which just stands for input-output manipulation. And then instead of putting a space in between each entry, you use this command, set width, and then you put a number in the parentheses. So what this command does is it says that whenever you print any entry, that entry must take up 5 spaces. So if you print the number 11, then 2 spaces are accounted for, and then you'll print out 3 extra spaces because 2 plus 3 is 5. So what this command is doing is ensuring that every time you print something, the number of spaces that item takes up is the same. So notice right now this 10 is basically above the 16. So let's see what happens when I run the code this time. Notice that everything is spaced out because, again, I want everything to take up 5 spaces. So 41, space, space, space. 42, space, space, space. Right, there are 5 total spaces there to be filled. Okay, when I scroll up to the top of this table, though, notice that it did better. Okay, this 10 used to be above the 16. Now it's over the 19. So at least this is better than what happened before, but it still isn't exactly what I wanted. So at this point, I don't know why my compiler is not printing this out properly. I spent an hour or two today and an hour or two yesterday trying to figure out what is going on with this. And I can't figure it out. When I copy and paste this exact same code into a different compiler, it prints the way I want it to. So basically I just gave up, and hopefully this command works for you in your compiler. Right? Most of you are using Visual Studio, so it should work in there. I don't know why it's not working for me in this particular compiler. It certainly worked the last time I taught this course, and I don't know what has changed since that. But anyway, at least it does better. But for you, this command should work. Okay, so all I say here now is if you want to use this set width command, you have to include the library IO_manip. And again, this n number right here, that's just how many spaces you want each entry to take up. So the larger you make this n value, the more spaced out your table will be. So let me, instead of having a 5 there, let me put a 7, and let's see what that looks like. So now it's even more spaced out. See? So the more spaced out you want your code, or sorry, the more spaced out you want your output, the larger you make that end value. Okay, so now let's talk about how you get input from the user. So we want the user to now give you values for the table. Well, basically, okay, this for loop right here in my current code is setting the values of the table, right? This nested for loop structure allows me to go row by row, and inside of each row, go entry by entry, and tell the computer what I want the value at that entry to be. So at position ij, I want the value to be 10 times the row number plus the column number plus 1. Well, if you would rather just get that value from a user, just add a cin statement. Right? That's all you need to do. So let's, I don't like having a 10 by 10 anymore. Let's let the user tell us how many rows and columns they want. Oops, columns. So let's ask how many rows. Let's get that from them. How many columns? And let's get that from them. Oops. Columns. Okay, now let's create an array with the row number they gave us and the column number they gave us. And now, oops, yeah, rows. Instead of going up to 10, because we don't know if it's 10 by 10 anymore, we'll go rows and columns here. So just to reflect that the user may have given us numbers besides 10. And so now, right here, let's now tell the user what value would you like to place in entry I, and then put a little comma in between, j. Okay, and then you'll get that value from them. So at the end here, I want to print this out to the screen. So let me, again, I don't know that there are 10 rows anymore, and I don't know that there are 10 columns anymore, so let me change these. So what this code should do is get a table from the user. So let's do a 3 by 4 table. Okay, let's do just 1, 2, 3, 4. So notice my first row, right? I is 0 in all these cases. So the first coordinate is 0, which means I'm in row 0. So 0, 0, 0, 1, 0, 2, 0, 3 are now 1, 2, 3, 4. For the next row, let's do 6, 7, 8, 9. And for the last row, let's do 11, 12, 13, 14. Now it will print it for me. Okay. And so again, I don't know what is going on with this output here with the set width thing not working, but whatever. Okay. But at the very least, it saved what I wanted it to, right? I wanted the first row to be 1, 2, 3, 4. I wanted the next row to be 6, 7, 8, 9. I wanted the next row to be 11, 12, 13, 14. And that's what happened, right? 1, 2, 3, 4, 6, 7, 8, 9, 11, 12, 13, 14. So if you ever want the user to be giving you things, right, to be giving you certain entries in your table, if you want them to fill in the entire table, you need to use a nested for loop structure like this. Most likely you do. I mean, if the table's small enough, then I suppose you could just have them do it entry by entry, but the easiest thing to do in general is this nested for loop. Okay, so that's how you can get a user to fill in a table. You just cin all the entries. Let's now do an example. So if A is a two-dimensional array, the transpose of the array is defined as the new matrix you get when you make every row of A into a column. So you start with a two-dimensional array like this, 2, 4, 8, 1, 3, 9, and the first row now becomes the first column. The second row now becomes the second column, and so on. If there were a third row right here, it would become the third column. That's how you form the transpose of an array. This is something that if you've taken linear algebra, you are comfortable with. but it's just a row and column swapping operation here. So let's write a program that gets an array from the user, and should be and there, right? And prints the transpose to the screen. So let me go back to my compiler here. This code right here gets an array from the user. So I get that, excuse me, I'm done with that, right? I've gotten the array from the user. But now we need to print the transpose, okay? So to do that, I'm going to just define a new array that I'm going to call my array transpose. And before I give it dimensions here, let's go back to this example and see what's going on. This is a 2 by 3 array, right? 2 rows and 3 columns. Notice that the transpose has 3 rows and 2 columns. Right? So there used to be 2 rows and 3 columns, 2, 3. Now there are 3 rows and 2 columns, 3, 2. So basically, when you take every row and make it into a column, you're swapping the number of rows and columns. So let's just define our transpose to reflect that. The number of rows of the transpose was the number of columns of the original array, and the number of columns of the transpose is the number of rows in the old array. Okay, so now down here, we've gotten the array from the user. Now we want to print the transpose, or sorry, let's first just initialize the transpose. Let's give it some values. So the way I'm going to do that is I'm going to go row by row and then entry by entry, just like I did here. But remember now, the number of rows in the transpose is the number of columns in the old matrix, in the old array. Okay, so this is going to look confusing, but remember up here, when you're setting up your nested your nested for loops, this number right here needs to be the number of rows, and this should be the number of columns. So in your transpose, this actually is now the number of rows. So I'm going to put that in the outer loop. And then in the inner loop, I'm going to now go up to the number of columns, but, oops, sorry, I forgot an I right there. But now the number of columns in the transpose is the number of rows in the original matrix. Okay, now I'm going to create the transpose matrix. So I'm going to say my array transpose. And if you want to tell it what's at position ij, okay, so let's go back to this example here. In this example, 2 is at position 0, 0. Right? So let me make this bigger. 2 is at position 0, 0 in the original array. Where is 2 in the transpose? Well, it's at position 0, 0 still, right? That didn't change. 4 up here is in position 0, 1. 0th row, first column, column 1. Where is 4 down here? It's at position 1, 0. So it used to be at 0, 1, now it's at 1, 0. What about 8? It's at position 0, 2 right here. But down here it's at position 2, 0. What about 9? Up here it's at position 1, 2. Right? Row 1, column 2. But down here it's at position 2, 1. So the relationship between the original array and the transpose is that you're just swapping the indices that keep track of position. So up here, if you're, mn, then down here you are nm. Right? So up here, if you're 4, 5, then down here you're 5, 4. So to reflect that in the code, let's just write that relationship like this. Right? Whatever this is and whatever this is, the relationship between the transpose and the original array is that you have to swap. You have to swap the two position indices. So ij in the transpose corresponds to ji in the original matrix. Okay, so now down here let's print the transpose. And again, the number of rows in the transpose is being kept track by this variable, and the number of columns is being kept track by this variable. And now let's print the transpose. Okay, so we're going to start by getting a matrix from the user, and let's just give it this matrix from my example. So there are 2 rows and 3 columns. So 2, 4, 8, 1, 3, 9 is the original array. And now look what it prints: 2, 1, 4, 3, 8, 9. right, which is the transpose. So to make sure this wasn't a fluke, let's do this again. Let's do maybe 3 rows and 4 columns. So let's do 1, 2, 3, 4. That's the first row, right, in the original matrix. And then 5, 4, 3, 2 is the next row. And then 6, 7, 4, 5. Right? Okay, so before I hit enter here, notice the first row is 1, 2, 3, 4. The next row is 5, 4, 3, 2. And then the final row is 6, 7, 4, 5. Okay, so notice the computer did exactly what I just said, except insert column for row, right? Now the first column is 1, 2, 3, 4. The next column is 5, 4, 3, 2. And the final column is 6, 7, 4, 5. Okay, so it's doing what we want, and the reason why it's doing that is because you just swapped, right? You swapped the two positions. IJ here is JI there, right? You did a little switch. Okay, so before I move on, let me just say again that these things take getting used to, especially if you're not used to working with matrices or tables. Again, it can be really confusing what this notation means. So my array transpose, just by itself, is the table. It is the two-dimensional table. And as such, you cannot write things like this. So if I try to write my array transpose, the computer won't know what to do with that. Okay, so I guess I can try this. Let's see what happens. So let's do a 2 by 3 here. 1, 2, 3, 4, 5, 6. Okay, so it prints the transpose and then it prints this nonsense. Okay, basically what it's saying is, I don't really know what you mean when you tell me to print the array. I do know what you mean when you tell me to print individual entries inside the array. Right? The computer is comfortable with that, with this statement here. So again, the difference between this kind of thing and this kind of thing is that my array transpose with nothing else written there is the entire table. My array transpose IJ is not the entire table. It's the entry inside the table at position IJ. Okay, so what's confusing here is that, first of all, you have a two-dimensional table. You have positions inside of that table, and the position is kept track of with two numbers, right? You need a row number and a column number. But in any case, you have a table with positions inside the table and then entries of the table at those positions. Okay, so it's easy to get confused about what things mean, right? Am I talking about a position? Am I talking about an entry at that position? Here's something else that maybe might go wrong for you. What about this? So now you're not outputting the table anymore, right? So it shouldn't be confused by that, but you've given it this bracket thing. So in some sense, you're telling it, hey, look, print this array at this position, right? At position I. And let me just, maybe it doesn't like the I. Yeah, sorry, it doesn't like the I because the I was destroyed at the end of the for loop. That's how for loops work. They destroy the variable counter. So let me just put like a 2 in there. Okay, so it stopped yelling at me now. So let's run this and see what happens. 2 rows, 3 columns, 1, 2, 3, 4, 5, 6. So again, it printed the transpose. It didn't have any trouble with this chunk of code, but right here it prints nonsense, right? So you might think, well, what's happening? I gave it a position, right? I said, hey, don't just try to print the table. I know I shouldn't do that, but print the table at a given position. All right, so what goes wrong? Well, what goes wrong is that this is a two-dimensional table. So if you want to print an entry inside that table, you must give it not only a row number, which is all you've given it here, right? Row 2. You have to give it a column number as well. You need 2 numbers to specify an entry. Right, so if this were a one-dimensional array, then this line of code would be fine. In a one-dimensional array, you only need 1 number to tell where something is. But in 2 dimensions, you need 2 numbers to specify where an entry is. Okay, so all of this is confusing until you work with it enough, until you've done this enough times. Okay, so let me briefly close by talking about higher dimensional arrays. So we've spent some time now with two-dimensional arrays, but you can have a three-dimensional array if you want to, a four-dimensional array if you want to, a 70-dimensional array if you want to. You can have as many dimensions as you want. Here's what a three-dimensional array looks like. So again, to declare it, you have to give it a data type. So, are you storing integers? Are you storing strings? Whatever. You give it a name, but since it's 3 dimensions now, you have to give it a number of rows, a number of columns, and then a depth, right? That's the third dimension there. So a 3-dimensional array is essentially a stack of 2-dimensional arrays. You have a 2-dimensional array at depth 0, a 2-dimensional array right here at depth 1, and a 2-dimensional array at depth 2, and so on. Okay, so a 3-dimensional array takes 3 parameters, right? Sort of like a length, a width, and a depth. That's what makes it 3 dimensions. By the same token, if you wanted to declare a 5-dimensional array, you would give it 5 numbers. You'd give it a length, a width, a depth, and then like a 4th dimension and a 5th dimension, whatever those correspond to. Now, of course, I can't give you a visualization of a 5-dimensional array. Okay, my ability to help you visualize stops with 3 dimensions. So a 3-dimensional array is a stack of 2-dimensional arrays. A 4-dimensional array is a stack of 3-dimensional arrays, but what does that mean? That's hard to visualize. If you can come up with a drawing, of a stack of 3-dimensional things in 4 dimensions, I'll give you a couple of extra points on your next exam, right, or whatever. Okay, so why would we care about higher dimensional arrays? Let me just give you one quick example. Suppose you roll 2 dice and you want to store all of the possible outcomes in an array. Well, all of the possible outcomes look like this. One die could roll a 3 and the other could roll a 2, or the first die could roll a 5 and the second die could roll a 4, etc. So if you only roll 2 dice, then here are the possible outcomes. Since there are 2 dice, it sort of makes sense that you have a 2-dimensional table right here, right? Each row corresponds to a single value on the first die, right? This is the row corresponding to rolling a 1 on your first die. This is the row corresponding to rolling a 2 on your first die, and so on. Okay, so 2 dice means that you can have a 2-dimensional array. Well, what about rolling 3 dice? Suppose you wanted to store all of those outcomes in an array. Well, it's hard to visualize, but essentially now, so this array here represents 2 dice. Okay, when you introduce a 3rd die into the mix, essentially if that 3rd die rolls a 1, then now you have 1 comma, and then you have this entire table essentially, right? You have 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 3, 3, 1, 5, 4, etc. So if you roll a 1 on your first roll, you essentially have a copy of this table with 1s at the front. If you roll a 2 on your first roll, you essentially have a copy of this table with a 2 at the front. If you roll a 3 on your first roll, you have a copy of this table with a 3 at the front. So in other words, you have something that looks like this, where you have 6 2-dimensional arrays. And the array up front corresponds to rolling a 1 on your first roll. The array next corresponds to rolling a 2 on your next roll, and so on. So you have a stack of 6 2-dimensional arrays. Okay, so that's one example. I'm not going to program it for you because I'm out of time here, but anytime you have basically something that needs 3 dimensions, or needs 4 dimensions, or whatever, the most natural thing to do is to have an array of the corresponding position. Okay, so like you physicists who do string theory, right? You deal with 11-dimensional space. If you want to keep track of a particle's position, or whatever you're keeping track of, right? If you want to keep track of position in 11-dimensional space, the best way to do that is with an 11-dimensional array, where the corresponding coordinate corresponds to the corresponding dimension. So the first coordinate is the first dimension, the second coordinate is the second dimension, etc. So there are all sorts of uses of higher dimensional arrays, and unfortunately we can't visualize them because we can't deal with higher dimensions. But that's it for this video.